All right, so our next speaker for the session is Michael Wood. Michael Wood, a very well-known contributor to the field of RQI, and he's going to talk about infrared acceleration radiation. Michael, whenever you want, the floor is yours.
Thank you for the introduction, Eduardo, and thank you so much for helping to organize the conference, and thank you to the other organizers for having me here. It's a real pleasure to be here. So this is work done in collaboration with Paul Davies, and it's up on the archive as a preprint with the same name, Infrared Acceleration Radiation. And when I say infrared, what I mean is low energy photons. In fact, I mean zero energy. So I mean soft particle production. And so to give you a little bit of context about the nature of this problem that I'm interested in, the first paper on soft particle production was in 1937 by Bloch and Nordseek. And I'd like to draw your attention to this last sentence in their abstract, where they found that the average number of emitted particles is infinite in such a way that the average radiated energy is equal to the energy radiated classically in a corresponding classical trajectory. So what they're looking at is a physical scattering process like beta decay, where the neutron turns into a proton and electron, and the electron accelerates away, creating some light. So what I'd like to do is present to you that trajectory and investigate a little bit about the acceleration radiation, and hopefully at the end of the talk convince you that, well, I'll save the surprise for you later. I'll convince you as I go along. So basically, there's a lot has happened in 80 years. But I'll just point out a few interesting developments. Well, in 1949, Chang-Falkoff found that a classical computation determines the total amount of energy radiated during beta decay from these photons. And they used this just as a heuristic in the nascent development of QED. But when you think about it, it's kind of amazing and just outright jaw-dropping that the total amount of energy could be computed using a classical theory, like classical electrodynamics, describing, beta decay, which is completely quantum, phenomenon, mediated by the weak force and all that comes with it, and all the Feynman diagrams that are needed to describe this interaction. So already we have something pretty interesting here, and it's related to the fact that soft particle productions occur for every scattering process known. So in *54, Lowe studied low energy particles and developed the first soft theorems. Jackson in '62 put in Chang and Falkoff's computation, the classical computation of the total energy of these photons in his graduate electrodynamics book. In '65, Weinberg generalized photons to gravitons for these soft photons to soft gravitons in the theorems that Lowe developed. And then from the '70s onward, we had experimental verification telling us that the energy emitted by the photons, or contained within the photons, if you will, is correct. So is confirmed by experiment, both in the energy distribution as well as the total energy. So I've drawn a little picture here to show you that it's the electron that is emitting the light. And this is the word for this is inner bremsstrahlung, inner meaning from the nucleus or inside the atom, and bremsstrahlung being the German word for breaking radiation. So, but the reason the classical computation works is because you can think of it as the electron emitting all the light. And so the 1, 2, 3 of this classical computation is that you use a step function to describe the electron, the velocity of the electron. That is, before some time equals 0, when the electron doesn't exist, the speed is 0. But then after some speed 0, some time 0, this velocity becomes this constant, some speed s. And so it's just the step function velocity. And if you plug that into the crank of classical electrodynamics, you can get the energy distribution and you can get the total energy emitted by the photons. Now that's this last equation right down here, where Q is the charge of the electron, S is the final speed of the electron, and delta omega is the maximum frequency minus the minimum frequency, this ultraviolet infrared cutoff that is encapsulated, the cutoff that you need that's for your detector sensitivity range that's encapsulated in this formula. So this has been experimentally observed. It makes up over 99.9% of the energy in most situations. It is, there are higher order QED corrections, but this is the lowest order QED inner bremsstrahlung soft particle energy creation, if you will. And this is the energy that I'm interested in. And the reason I'm interested in it is because I'd like to look at this from not a classical point of view and not a QED point of view, but a semi-classical point of view using a moving mirror, which has a lot of deep similarities to the moving point charge. So the Lamar formula that we all learn and love for the power emitted by an electron is scales according to acceleration squared, and the same scaling for the power of a mirror, except the mirror is quantum and the electron is classical. If we look at it goes to the self force too, where you take the derivative of the acceleration as well. So there's a deep connection between mirrors and electrons, and I'd like to use the mirror model to describe this electron. And so a little drum roll, I'm going to propose the trajectory right here. It's globally defined and continuous, and you need not really worry about what it is. I'm just going to skip through the dynamics here and just let you know that if you use this new trajectory, that you can make time-dependent predictions that in principle can be tested, namely the power distribution and the total power emitted. This is not possible in QED. It's a nightmare and notoriously well known for being horrible for computing time-dependent quantities of interest. But now with this continuous trajectory, we've got time dependence in the problem. So this is the new stuff right here. And it's quite consistent because if you integrate over a coordinate time, you get the energy emitted by the electron. So, but the real surprise, the real kicker here that I'm so pleased to present to you is that if you look at the power when the electron is moving really fast, when S is close to 1, the speed of light, you get a nice flat plateau indicating some sort of equilibrium situation. And the same thing for the self force. But so it's clear that the radiation is distributed according to the Planck factor, which means that the photons have a temperature, and in the same sense that a black hole has a temperature because the particles emitted are Planck distributed, or the universe has a temperature because the photons in it are Planck distributed, a single electron has a temperature. And so if the plateaus are not enough to convince you, you can use the moving mirror model to compute the Bogoliubov coefficients, which also integrated appropriately give the same confirmed, experimentally confirmed energy. And the temperature here is kappa over 2 pi, where kappa is related to the charge of the electron and the UV and infrared cutoffs associated with the problem, or the system, if you will, the scale of the system. So the temperature here is 24 alpha over pi. Alpha is the fine structure constant. That's E squared over H bar C, 4 pi permittivity of the vacuum. KB is a Boltzmann constant, and E gamma is the UV minus IR cutoffs. So, so that's the real surprise here. It's quite interesting to see that inner bremsstrahlung has a temperature that a single electron you can think of as being subject to this. And that there can be a kind of idea here of electron thermodynamics, if you will, appropriate to the acceleration scale of the system. So the points I'd like to make is that inner bremsstrahlung is an analog example of the dynamical Casimir effects. This is kind of like a post-diction since the data already exists. Inner bremsstrahlung is experimental evidence of the self-force, which is absent for a classical moving point charge, and that there is a universality associated with this temperature because soft particles are produced for every physical scattering process. So therefore, this soft particles can be characterized by a very particular equation of motion. Moreover, since the dynamical Casimir effect, the moving mirror model has an exact an analog to black hole particle production.
2 minutes, Mike, 2 minutes.
Great. There is an analog space-time, so where the particles produced from the space-time will be soft and will have the same temperature. So we hope to study this soft space-time in the future. So thank you for your attention, and that's all I have to say at this point.
Thank you, Mike. As usual, it's a pleasure to have you. We have time perhaps for 1 or 2 questions, depending. I don't know who was first. I saw the 2 hands appear simultaneously from my reference frame. So I
think Robert was slightly earlier. I think Robert was slightly ahead of me.
All right, let's go with Rob. Rob, let's go. You first.
Yeah. Hi, Mike. Yeah, that was very interesting. I see the result. I didn't quite get all the methods. What I'm wondering is, how much does this care that you're dealing with an abelian gauge theory? Could you extend this to non-abelian Yang Mills, for example?
I'm not so sure. The relevance, it's completely, you can think of it as completely classical electrodynamics, where you just pick out this trajectory for the electron motion and just use moving point charge radiation results. And the only thing that really requires semi-classical physics is this beta coefficient up here. So I don't believe you need to use anything too much more sophisticated than the Bubulubov mechanism here with respect to getting the spectra. So getting the spectra does require the semi-classical analysis and then making a connection between mirror as an analog system for the electron, treating the electron kind of like a tiny mirror, if you will. I mean, so this may not be the spectrum, even though it gives the right energy. It's just kind of probably the case that this is the spectrum.
All right. Well, I just think, I mean, if it could be understood, then quarks in the early universe would have a color temperature analogous to the way that electrons have an electromagnetic temperature in your language. That's what I'm thinking. But
it would be very interesting to look at. Actually,
well, maybe we could talk about that later if it could work, right?
Yeah, let's look at that, because I had only thought that of maybe gravitons, but since it corresponds to, it can correspond to very many different systems. So I would like to look at that. Yeah, thank you.
Anyway, thanks. Good talk.
Mike, are you gonna stay around for after the session finishes?
I will.
For questions? But
yes,
then, Albert, is it okay to move yours for them? Because the next speaker is also from Australia as well.
That's okay.
Perfect. So let's have if you're here, if you can make it in the after the break, and let's thank Mike again for now to move to the next talk. Thank you very much, Mike.
So my question, I guess it's more of a general question, maybe has a simple answer, and it probably might be same kind of answer to a similar question if one consider, or maybe that's even the case in some sense, that equivalent to what you were doing, of having an accelerated mirror for a finite time. So the question is the following. So you were talking about this sort of thermality, this thermal distribution. In many cases, if you start with a pure state, in this case, for your photon vacuum, thermality is connected with the fact that you look at a subset of the modes and those are correlated with other modes, and that's how you can understand thermality being a sort of mixed state arising from an initial pure state. So in this case, should I understand that as some kind of correlations between photons emitted at different times, or where?
That's a real nice. That's a real, yeah. You're hitting on the crux of the issue, actually, with the respect to the definition of thermality and this. So let me say that the beta coefficient, the beta Bogoliubov spectrum, you know, it has that Planck factor in it, but you know, there's other factors around it, and you know, multiplied by it, and it's not a Planck spectrum, but it is a Planck spectrum to leading order when the electron is fast. So when the final speed of the electron is near the speed of light. So in leading order. So it's always quasi-thermal. So information is preserved. It's unitary. The pure state goes into a pure state. There's no you know, actual mixed state. It's only to leading order. So in that sense, you know, I guess it's a good thing, because you know how you have to kill. Most people agree that you know, information preservation's the way to go. But we do have to loosen our definition of you know, thermality. It's quasi-thermal.
But even to leading order, I mean, do you see? So, for example, if I truncate to that leading order and I neglect subleading corrections, then would I have thermality in the sense of a mixed state for a subset of modes, and then the correlations are hidden in these subleading terms? Is that what you meant, or?
Yeah, no, I think that's
okay.
Exactly right. Yeah, and yeah, there's some subtleties to it. It's actually, you know, it's a Planck distribution, even to when you compare one mode to another mode, like the incoming mode to the outgoing mode, and when one is larger than the other, or vice versa. It's actually a Planck distribution in both regimes.
Because the fact that one has a beta coefficient that looks, you know, that has this factor that looks like the Planck, it could still be, you know, the Bogoliubov transformation is a unitary transformation. So it could be that you have just this factor with this frequency dependence, but it's still giving you, you know, just a unitary connection between the two. In other cases where thermality arises for these situations, it's because you really look at the subset of modes. And then, you know, the peculiarity of the form that you have for the beta coefficients in the Bogoliubov transformation, plus the fact that you look at the subset of modes, that's where you have then this mixed state with thermal type distribution.
Yeah. Okay. I like the idea. Yeah, when you truncate it, then you could call it mixed. I think that's usually
exactly. So that's, but in fact, even, you know, beyond maybe the particular case you were discussing here for the acceleration of the electrons and so on. I mean, I guess maybe I had never really thought that much about it, but if you have an accelerated mirror, but just, you know, for a long but finite time, I wonder whether one could also, you know, if it was infinitely for an infinite time, then again, you have these two set of modes, and I think you can understand thermality in this respect, that you have the modes that, you know, that go to in the other, you know, to the opposite sort of scry, and there again, I think you can understand their thermality as, you know, being in a mixed state for one subset of modes, because the other modes that just escape, you know, if you trace those out. So that was my understanding for an eternal or an eternally accelerated mirror. But if you have the mirror accelerated for a finite time, sufficiently long, you would expect that you see maybe something similar for a finite time, similar to thermal, but not exactly thermal. And presumably there, one might see these correlations between photons emitted at different times that would, you know, restore purity of your state. It's just that, again, there maybe the tracing out in practice was, if you just look at photons emitted, you know, for a finite time, and neglect their correlations with photons emitted maybe at different times, that you would kind of see this effective thermality for approximate thermality for a finite time. So I don't know if you agree with that.
I'm liking what you're saying, but however, when you say finite time, well, yeah, you mean, I think actually the way I would phrase it is that the acceleration asymptotically goes to zero. So
yes, that's what I meant. That's what I meant, that after a finite time, the acceleration, goes to zero. Yes.
Cool. Yeah. All right. Yeah, I like it. I like it.
But then, so that was as far as finite acceleration for a finite time. But then I was also referring, by looking at the field and just looking at the radiation emitted, for a finite time, maybe it looks approximately thermal and mixed. But presumably, if you had access to all the information on the radiation that is emitted, for arbitrarily long time, in that case, it should be a pure state, and presumably it's correlations between different emissions at different times that would restore purity, I suppose.
That reminds me, Magdalena was talking a lot about the proper time trajectories, and I have not actually looked at this trajectory in proper time, but it could be that maybe it's literally truncated in proper time rather than say some asymptotic infinite proper time trajectory. But I think that would be a nice thing to do, because I think all of it is tractable. It's all quite tractable for this trajectory, so it'd be nice to compute.
Right. In fact, I guess I'm a mistake, but I was now even kind of I thought that you had in some earlier conferences some time ago discussed cases where you look at the sort of analog of the information paradox problem with the accelerated mirror, where presumably you were maybe looking at very related things, I suppose.
Yeah. Usually with the one plus one dimensional context, and this one, it looks, you can actually go to treat it, in 3+1 if you take both sides of the mirror, which is, it seems like there's a little bit of hope for other dimensional contexts if you include both sides of the mirror. So that seems to be the key in that respect.
But did you analyze back then the cases of a mirror which is accelerated for a finite time?
Well, actually, not strictly finite. All the trajectories that I have looked, so that would
but if it's asymptotically, if it becomes asymptotically, I guess that would also be fine. Yes.
Oh, okay. So if it's in fact, those are the ones that are, I think, maybe arguably the most physical, because they, the unlimited motions give a lot of pathologies. Infinite energy, infinite particles, infinite radiation.
Right.
And so the ones that are asymptotically inertial are wonderful. They're lovely because they have this finite, all sorts of finite things that can be computed and preserve information. So
right. So that's why I was thinking of that, because in that case, presumably again, the question would be, if it was accelerated, asymptotically goes to zero acceleration, but it was accelerated for a sufficiently long time, one would have expected to see something similar to thermal radiation for a finite time being emitted. But then overall, it should again be a pure state. So presumably again there, maybe one could see that there is information hidden in the correlation between emissions at different times, presumably that would help to understand how unitarity is restored.
Yeah, there's some nice work to do.
Yeah, I guess so. Yeah. Okay. Well, thanks a lot. It was thanks for your answers, and it was an interesting discussion.